Okay, we're back in business. Okay, Ionic Compounds is the title. And I'm just going to bring up all of this animations. I'm not a fan of the animations. I don't even know why I have them in there. Okay, good. This is the type of stuff that we're going to be doing today. It's important that we can see a periodic table in order to make sense out of it. So I'm just going to give you guys all the periodic table here, and you can just leave that with me at the end of class. All right? There's periodic tables. So there's periodic tables. Just send one back. Now, in order to be able to understand these and understand this stuff correctly, we need to keep in mind what we've learned about the periodic table. Chemistry is the type of subject that continually builds on what we've taught you in the past. You can see as you're writing, we're talking about metal atoms and non-metal atoms. We learned about that when we learned about the periodic table. You can also see in that statement that we're talking about the electrons that are being transferred or given away. We learned about that the last couple of days when we talked about some atoms giving their electrons away and other atoms that were gaining electrons. That's what that ion sheet was about, giving electrons away and gaining electrons. So we need to keep in mind those two things in order to understand this. I guess just to kind of prepare our minds, on your table, or even on my table up here, where do I find the metals and where do I find the non-metals? A little bit of a review. Where do I find the metal atoms? Where are they located? Brett. Metal atoms, where are they found? The stair-step line separates them. So where are the metals compared to the stair-step? On the left. Excellent. Good job. On the left. So an example of a metal atom is like potassium, right? How many dots does potassium get in a Lewis diagram? Lucas, how many dots does a potassium get? Nope. 1. It's in group 1. This is why I ask questions like this, to get our brains back rolling again. 1. So when potassium wants to do something with its electron, it's going to lose 1, right? And when potassium loses 1, what does the charge become? When it gets rid of 1 negative feeling. Remember negative feelings, my hippie explanation? What does the charge become, Tyson? If it gets rid of a negative 1 or a negative charge, if it gets rid of a negative feeling, what does that become? It becomes positive. And because it got rid of 1 electron, positive 1. All right, positive 1. So metal atoms lose their electrons and they become positive. Non-metal atoms, well, let's talk about chlorine. How many dots does chlorine get? How many dots does chlorine get? Not 17, but you're close. 7, because we ignore the 10. 1, 2, 3, 4, 5, 6, 7. How many electrons is stable? How many electrons does the atom want? Yep, 8. So what's this chlorine going to do? Well, what's the chlorine going to do? Yep, gain 1. Cl, 1, 2, 3, 4, 5, 6, 7, 8. And what charge does something like that become? Negative 1. Excellent, negative 1. We talked about the formation of ions. An ionic compound happens when 2 ions like this get together. All right? Now, in grade 9, you learned a little bit about static electricity. The analogy I like to use is magnets. What's holding these 2 magnets together? Tyson, what's holding them together? No? You ever play with magnets? And so it either sticks or it doesn't stick, pushes away. Why does it stick? Do you know? Oh, interesting. The question was, is there a positive or a negative? Now, in magnetism, we don't use the term positive or negative, but you're right. It is essentially a positive and a negative. What do we call these positive and negatives when it comes to magnets? We don't normally say positive and negative, but you could think of it that way. Yep. It is a magnetic field. What do we call the ends of the magnets? No, they're not terminal. What do we call the ends of the magnets? You know? It is attraction. It's correct. We call them poles. Have you ever heard of the magnetic poles? All right? Not like the poles on the Earth, but like a magnetic pole. We also call it north and south, like on the Earth. Have you heard of that before, maybe? North and south? And opposite poles attract. They stick together. We could call them positive and negative. The physics wouldn't change if we called them positive and negative. Opposite poles attract, just like opposite charges attract. If I were to bring that positive potassium ion close to that negative chloride ion, what do you think they would do? They would stick together. That's what an ionic compound is. When the opposite charges of an ion get close enough together and they stick together. All right? So there's charges in those ionic compounds sticking the ions together. Notice here, I've got sodium on the left. It's a metal up against a chlorine or a chloride, non-metal. The sodium would be +1, just like the potassium. The chloride, -1. They stick together, form an ionic compound. Here I've got copper on the left-hand side, a metal. And here I've got a bunch of non-metal atoms. This grouping of sulfur and oxygen has a special name. It's called a sulfate. We'll learn about that in a couple of days. It doesn't matter. It's a group of non-metals. When you have a metal with a non-metal or a metal with a group of non-metals, you have opposite charges. They attract, they stick together, and we have an ionic compound. All right? So an ionic compound is caused by these ions attracting each other. And here you can see this is a little animation. It's kind of an old one, so it keeps repeating. It's a repeating situation until I change the screen. But here you can see the sodium's atom, the sodium's electron moves over to trade with chlorine so that the sodium gives it to the chlorine to make it become chloride, and then we have those ions and they stick together. So it's a transfer of electrons. And here again, we've got, again, a transfer happening. You can see another animation. The electron is given up. It makes it become positive. The chloride becomes negative, and they stick together. All right, let's do some examples. Here's where you're going to need your periodic table to help you draw these. We want to draw this out. I'm going to do 2 or 3 examples, and then I have the worksheet for you to work on. All right? And again, we haven't used a lot of time in class. I'm going to let you work on that worksheet completely. When you get it done, you could then work on any of those other things that aren't done, and maybe we could even get the lab started. You know what I mean? We'll get it in a couple of chunks. So let's write down these examples, and then you can then work on the sheet. So, forming ionic compounds, Lewis diagrams. As soon as I ask you to draw a Lewis diagram, it means we want the dots or the charges. That's what the Lewis diagrams are. So I'm going to do this right on the screen. So I'm going to start with a sodium and a chlorine. So periodic tables, track down a sodium on your periodic table. It's going to be a metal because we're doing ionic compounds. Somebody tell me the symbol, and somebody tell me how many dots I'm going to put around that sodium. Yep. Na and 1 dot. Na with 1 dot. Again, remember, we're dealing with 1 dot, 2 dots, 3, 4, 5, 6, 7. And how about the chlorine? Oh, we've seen that one. What do you got? Yeah, Cl with 7. We just saw that a minute ago. That's okay. Cl with 7. 1, 2, 3, 4, 5, 6, 7. Well, this works out quite nicely. They're kind of a good match. Why is this a good match? Why is this a good matchup? Max, what do you think? Yeah, it's perfect. This is a good matchup. I'm going to put an arrow here. I'm going to just use a different color. You can just use whatever color that you've got. And so the sodium losing allows the chlorine to gain. Now I'm simply going to draw their ion pictures, just like I drew them over there. Sodium got rid of 1. So when sodium gets rid of 1, pushes that negative away, what charge does the sodium ion become? +1. And I'm not even going to put a plus. I'm going to put the chlorine right beside it. Now, a very important aspect of drawing these diagrams is that I have the exact same amount of electrons that I had at the beginning than at the end. How many dots in total are on the left-hand side of this arrow, this reaction arrow? Yep. So how many dots am I going to need on the right? I have to have the exact same because I can't lose any. And that works perfectly. That means once the chlorine has gained 1, I've got to put in my 8 dots. What charge does that make this when it gained 1 electron? Justin, what charge does the chlorine become when it gains 1 electron? What's the charge on an electron? Negative. So it's gaining 1 extra, so it's going to be, I don't know. We're close. We're close. How many electrons is it gaining?
None. I don't know.
Okay, let's slow down the truck here. Let's back it up. We're gonna back it up for you. Are you watching up here? Okay, let's look up here. How many dots does this chlorine have? That's okay. It's okay. We'll solve this problem. Not an issue. Are you going for glasses? Well, how are we going to solve this problem? No, I'm not. I'm not giving up on this. This is happening. Focusing on me. Seven. How many does chlorine want to get? 8. So how many electrons is it going to gain? 1. And this 1 brings a negative with it. So what's the charge going to be on this thing after it gained 1 electron?
9.
The charge is the sign on that electron. It's not the number of them. It's the sign on it. -1. Whew! That's a workout, isn't it? That was a workout to get that information. I might have to reposition you in the class. I think that might have to happen. Okay, let's now name this thing. Sodium is a sodium ion. So this is sodium. Same name. When we get a negative ion, remember, what does it end in? Yep. Chloride. Sodium chloride. So I already did the name. Don't worry about that. We've done the name. Chemical formula. The chemical formula for a compound tells us how many atoms of each type are in it. Because there's 1 sodium and 1 chloride, we write it as NaCl. We're going to be putting little subscripts down here to tell us how many atoms of each type there are. But when there's 1, we don't put a 1, we leave it. We assume it's a 1. So Na1Cl1. That's the formula for that substance. Let's do another example. Goodness. Justin, you ready for another example? Ready for another workout there? No? Oh, man, that's no fun. Didn't you have fun? I had fun with that. Look at the size of that chloride on the board. It's the biggest chloride I've ever drawn. Pick your atoms. Calcium. Did you find it, Lucas? What's the symbol? Ca. Are you afraid now, Lucas, now that I put on that performance with Justin? A little bit? Nice. How many dots, Lucas, does Ca get? Correct. Tyson, what's the sulfur symbol? S. And how many dots does it get? Remember, what row is it in? We're looking, yeah, 6, very good. 1, 2, 3, 4, 5, 6. Now, I draw them as being by themselves because that's really the way they exist. You could maybe draw them together. It's not a bad deal. Hey, this is a good setup too. Why is this a good setup? Why is this a good setup? Yep. And calcium has 2. 2 arrows. There, there. I'm going to draw it down below because I want a little bit of extra room. Calcium has no dots around it because it got rid of its 2 electrons. So now I'm going to have somebody think about the charge. It got rid of 2 electrons. What's the charge? Logan, what's the charge? +2. Nice. Again, notice 8 dots in total. Sulfur's got to have all of the dots. What charge is the sulfur? Yep. -2. What do you think the name of this stuff is? There's a trend here. It is related to the last name as well. What do you think the name is? Yep, Pat? Yeah, very good. Calcium sulfide. Calcium sulfide. Calcium sulfide. Sorry, the F and the I got squished together there.
Is it always I at the end?
Yes, the non-metal always gets an "ide" at the end. It's correct. Yep. And that's if they're binary. I'm going to teach you naming a little later on, but yes, for now, yes. What's the formula? How many calciums and how many sulfurs? This is pretty straightforward, this one. Yep. We don't put the charges in the formula. We just are counting the number of each of the atom types. CAS, one Ca and one S. In a moment, we'll do an example where we're going to have 2 or 3 of those. Okay, excellent. Let's do another one.
So if it's a compound that last letter is capital?
Last letter. Ooh, you mean the name?
Yeah.
Yeah, because it's the 2 symbols that are put together. It's the symbol for calcium and the symbol for sulfur. So because the symbols have to start with a capital, right? I have capital and lowercase a for calcium and capital S for sulfide. So I'm literally putting the 2 symbols together. The symbol for calcium and the symbol for sulfur. Okay? So yeah, it has to be a capital. Yeah. Because it's the symbols for the individual elements put together. Okay? I'm hoping we're seeing a little bit of a trend. I'm hoping you're able to find lithium, determine how many dots, find oxygen. Looking for some assistance on dots, and I haven't picked on Mitchell yet. 1 dot, nice, and oxygen is 1, 2, 3, 4, 5, 6. Not so much a match made in heaven. But we can solve this. When a chemical reaction takes place to form a compound, it's not that there's only 2 atoms hanging around. There are actually billions and billions and billions and billions and billions and billions and billions of atoms in a chemical reaction. So it's not like the oxygen has to hang around and say, oh no, I don't have enough. There's going to be all kinds of atoms around. So what can we do to fix the issue here? Any ideas? Add another lithium. Because lithium only has 1 to give away, we're simply going to draw another lithium. So 2 lithium atoms are going to be needed to take care of the oxygen. Because oxygen needs 2, and lithium only has 1. So when the match isn't so nice, we simply add enough of them in order to make it work out. So 1 lithium is going to give it there, the other lithium is going to give it there. So I'm going to draw 2 lithium ions. Because it's lost 1 electron, it's +1. You could draw them in a row. That would be fine. But in textbooks, they tend to put them on opposite sides, right? And I really don't care. You could put 2 in a row, but in reality, the lithium ions stick to the opposite sides of the oxygen, like the 2 magnets would be stuck to the outside. I still need my 8 dots, and I need a charge on the oxygen. What's the charge on the oxygen going to be? Yeah, Kate? -2. And notice what happens to the charges. How would you describe all those charges in that entire thing? What did the charges do? I got 2 +1s and a -2. What could you say that those charges did? Any ideas? They made it neutral. They canceled everything out. It made it become a neutral thing. That's good. The name of this stuff. Again, the name is no different, even though I've got them spread out, the name is the same. Lithium oxide. Because it's got to have "ide" on the end. And the formula. The formula. Yep. Li with a little subscript 2 and O. The metal always comes first and the non-metal at the end. All right? Lithium oxide. Do I have one more example? Yeah, let's do one more and then I'll let you work on the worksheet. How many dots on the aluminum? You getting the idea?
3.
And how many on the fluorines?
7.
Yeah, 3 and 7. Now, aluminum wants to get rid of everything. Fluorine can only take 1. What am I going to do to fix this issue? Yep. I need 2 more fluorines, right? Because if fluorine can only take 1 and aluminum's got to get rid of 3, we're going to need 2 more fluorines. Because each fluorine can only take 1. Again, the textbook drawing would have the aluminum in the middle with the fluorines around it. But I'm okay with drawing individual fluorines all in a row. So if you were drawing this out, I'd put fluorine. It's 8 dots now that it's got an extra electron, -1. Another fluorine, -1. Another fluorine, -1, because they're only gained 1. And then the aluminum. Charge on the aluminum? Charge on the aluminum. What do you think, Tyson? Yeah, +3. It's got to cancel out, right? +3. Name of this thing. Metal first, non-metal second. Name of this thing. We'll pick on Bella at this point. What's the name going to be? You always put the metal first. Yep, aluminum fluoride. Aluminum fluoride. And what's the formula of this? Max, what do you think? The formula of this thing? AlF3. Okay? All right. Okay, so that's the extent of the lesson. We've got about 40, well, maybe not quite 45 minutes, a little less than that. Let me just switch over to Google Classroom. Some of you already started to look at that, which is just fine. You'll notice here on Google Classroom, I've got a little formation of ionic compounds practice sheet. You can do that right on your device, as you know, or you could do it on a piece of paper. This is exactly what we did. I'm not doing anything different than what we did in our notes. You're going to draw the atoms, Mg and O, show the transfer. You can imagine that the arrow is in between this box. And then you'll draw the compound with the brackets and their charges. You'll write down the chemical formula, and you'll write down the name. Okay, so you're working on that right now. If you get done that and you haven't finished the ions sheet, you can work on that. If you haven't finished your testing for ions lab, you can finish that. So we've got lots of work to work on. I'm going to stop the recording. And